Section: Introduction. In this section, we introduce the importance of personalization for interactive agents that aim to promote positive behavior changes, particularly in health and lifestyle. We recognize that evaluating the effectiveness of these agents through user interactions can be expensive and time-consuming. To address this, we propose a comprehensive framework for creating groups of synthetic users based on health, lifestyle, and behavior, allowing them to interact with coaching agents. Our framework is versatile and can be applied across various health and lifestyle areas, which we validate specifically in sleep and diabetes coaching. We focus on generating synthetic users using large language models, LLMs, that reflect real demographic and health data. Unlike previous studies that aimed for general alignment, we target a specific application where these synthetic users interact with specialized health agents. We outline our approach, which involves creating natural language descriptions, or vignettes, that represent users' demographics and health conditions. Additionally, we can incorporate specific information like barriers and goals, challenges from behavioral models, or detailed backstories for the synthetic users. Using these vignettes, we can simulate realistic interactions between users and coaches through direct LLM calls or generative models like the Concordia system. We demonstrate the effectiveness of our method in sleep and diabetes coaching, ensuring that our synthetic users exhibit behaviors and health conditions that align with their assigned attributes. We validate this through evaluations by trained human experts and by comparing our synthetic users to generic ones. Furthermore, we show how our synthetic users can help assess coaching agent performance by identifying flaws in their behavior, such as irrelevant suggestions or repetitive questions, through user experience feedback. We also review previous work that utilized patient simulators to evaluate nutrition coaches, noting limitations in demographic and clinical representation due to a small sample size. In the background section, we explore the development and objectives of LLM-based synthetic personas, detailing their application in health contexts and the software systems used for simulating agent interactions. We also discuss challenges associated with using LLM-derived synthetic users for agent development. We highlight the need for auto-evaluation in LLM agents due to the high costs of human evaluation, leading to the concept of reinforcement learning from AI feedback, RLAIF. This method uses LLMs to assess other LLM outputs, ensuring alignment and helpfulness. We note that synthetic personas can be created from census data to build evaluation datasets, allowing for more specific user modeling. Additionally, we emphasize the importance of modeling personality traits in LLMs, as they significantly impact communication effectiveness and user interaction. Section Summary. In this section, we introduce a framework for generating synthetic user cohorts that realistically simulate interactions with coaching agents in health and lifestyle domains, specifically validated in sleep and diabetes coaching. Our approach utilizes large language models to create detailed user profiles based on real demographic and behavioral data, enabling effective evaluation of coaching agent performance and addressing user-specific needs and challenges. Section: LLMs and synthetic personas in health. In this section, we explore the use of large language models, LLMs, and synthetic personas in health contexts. Several studies have suggested using LLMs for health and wellness advice. One notable example is the Articulate Medical Intelligence Explorer, AMI, an LLM agent created for conversational medical diagnosis. AMI demonstrated impressive results, achieving higher diagnostic accuracy than primary care physicians in a randomized study. It was trained through self-play using simulated doctor-patient conversations and tested by searching for medical conditions across 3 databases, followed by internet searches to gather relevant information on demographics, symptoms, and management. We utilized PaLM-2 as the foundational model for all agents, including patients and doctors, who received specific prompts for their roles. We fine-tuned both patient and doctor models using real doctor-patient interaction datasets and dialogues generated through self-play. A moderator agent facilitated the conversation and determined when it concluded. However, the AMI study faced limitations in its synthetic patient design. For instance, Retrieving symptoms and demographics from online discussions could introduce bias, as those engaging online may not represent the broader population. Additionally, online discussions might misattribute symptoms or provide incorrect mitigation strategies. The model also did not control for personality traits, relying instead on the distribution found in online discussions, which may not reflect the target demographics. Furthermore, the fine-tuning of POM2 might make the patient agents appear more agreeable and communicative than actual patients. In contrast, our approach employs Concordia to manage interactions between the health coach and the synthetic persona, rather than using a general-purpose LLM. We referenced several datasets for medical conditions, including the Health QA dataset with 613 common conditions, the Malacards Human Disease Database with over 18,000 less common diseases, and the MedicineNet Diseases and Conditions Index with around 4,600 conditions. We created 4 agents: doctor, patient, moderator, and critic, with Amy fulfilling all roles and Concordia acting as the moderator. We also examined the application of LLMs to simulate patient populations based on medical histories from 1,495 patients in the MIMIC-3 database. This method represented each patient's medical and demographic information as a knowledge graph, which included over 15,000 nodes and more than 26,000 edges. The patient information was retrieved from this graph in response to doctor queries and expressed in natural language, with tone adjusted according to the Big 5 personality traits. A key finding was that patient LLMs, using structured representations of patient traits, communicated symptoms and history more effectively than those relying on unstructured clinical notes. Our work differs significantly in a few ways. First, representing individuals as knowledge graphs is more suitable for clinical settings, where unstructured notes need organization. Thus, we focus on constructing the graph and retrieving information accurately. However, this graph representation may not be ideal for wellness settings, where users' needs are less structured. Second, the generation process can only navigate the existing patient graph and cannot create new individuals, which may limit privacy and scalability. We employed a reasoning retrieval augmented generation (reasoning RAG) workflow with a knowledge graph from the MIMIC-3 database. This involved developing a knowledge graph from 1,495 patient records, containing a vast number of nodes and edges with various medical entities. 6 agents accessed this knowledge graph, with 2 querying it, 2 verifying the results, and a rewrite agent considering the Big 5 personality traits. Without the reasoning RAG and knowledge graph, performance significantly declined. Lastly, we discussed using synthetic personas to evaluate an LLM system for collecting patient histories in medicine. The patient agent was instructed not to display medical knowledge or generate new symptoms beyond the provided case vignettes. We considered 2,000 case vignettes, focusing on evaluating the information gathering and diagnostic capabilities of LLMs rather than coaching. Unlike our work, this study did not ensure that patient profiles were representative of the general population, nor did it model personality types in generating patient dialogues. Section Summary. In this section, we explore the application of large language models, LLMs, like Amy for conversational medical diagnosis, highlighting its superior diagnostic accuracy compared to primary care physicians. We also discuss the limitations of synthetic personas in health settings, including potential biases in patient representation and the challenges of accurately modeling personality traits, while contrasting our approach with existing methods that utilize structured knowledge graphs for patient information retrieval. Section: Generative Agent-Based Models. In this section, we discussed generative agent-based models, specifically the Concordia system we utilized for simulating user personas. Concordia provides a framework for creating agent interactions, especially dialogues, based on a detailed backstory. It has several important features for our research. First, it uses associative memory and logical reasoning to ensure that what agents say is connected to the backstory. Second, it incorporates metadata tags in prompts to clearly define different contextual elements, such as agent memory, observations, previous conversations, and overall goals. We can also assign different levels of importance to these elements, which helps guide the language model in generating relevant dialogues. Third, Concordia offers extensive logging capabilities, allowing us to closely examine the internal processes, including the prompts sent to the language model, the reasoning steps taken, and the final outputs. Fourth, its modular design lets us customize the agent pipeline by swapping out components as needed. A key requirement for these simulation frameworks is the ability to manage multiple changing states in the interaction environment, as these can greatly affect an agent's actions and speech. Importantly, the changes in these states should be driven by logical reasoning. Concordia meets this need by providing code abstractions that help us integrate and manage these dynamic states effectively. Next, we address the challenges of using synthetic personas derived from language models. While these models are trained on vast amounts of data, they often misrepresent subpopulations and health conditions. The fine-tuning process can further skew the outputs. To tackle this, we propose a comprehensive framework for generating synthetic users based on real human data, including demographics and health characteristics, to accurately reflect a target population. We can sample this real cohort uniformly or adjust it to highlight underrepresented groups. From this cohort, we can add additional health conditions and rich backstories, creating a detailed vignette for each synthetic user. In the following sections, we explore how these vignettes can facilitate interactions between synthetic users and coaching agents in two health coaching scenarios, sleep coaching and diabetes coaching, using two independently developed coaching agents. For our sleep coaching experiments, we recognize the importance of sleep for overall health. Insufficient sleep can negatively impact cognitive function, mood, and various health aspects. Sleep disorders are common, with significant percentages of adults reporting sleep difficulties. To create synthetic users with realistic sleep conditions, we use the LifeSnaps dataset, which includes participant demographics, sleep data, and psychological assessments. We focused on key demographics and health attributes, including sleep duration and variability, which are crucial health indicators. We generated a synthetic sleep profile for each individual in the dataset based on their real demographics and sleep characteristics. This profile includes attributes like primary sleep concern, sleep goals, reasons for those goals, and barriers to achieving them. We then instantiated each synthetic user in Concordia as a simple LLM agent, ensuring clarity and reproducibility by including the entire conversation history and backstory in the prompts for generating each response. Section Summary. In this section, we discuss the use of generative agent-based models like Concordia for simulating user personas, emphasizing its features such as associative memory, contextual metadata, and modular architecture that enhance dialogue generation. We also outline our framework for creating synthetic users based on real demographic and health data, which we apply to generate sleep profiles for health coaching scenarios, ensuring that interactions are grounded in realistic user characteristics. Section: The Sleep Coaching Agent. In this section, we describe our sleep coaching agent, which is based on a two-agent system featuring a talker and a reasoner. The reasoner, or System 2, creates an internal model of the user by analyzing conversation history and planning actions, while the talker, or System 1, generates responses based on the reasoner's structured state. We utilized Gemini 1.5 Pro as the language model engine for both agents. To evaluate how well our coaching agent interacts with synthetic users, we explicitly modeled the user's internal state and compared it to a predefined sleep profile. After a 10-turn interaction, the agent identified the user's main sleep concern with an accuracy of 89.7%. For barriers and sleep goals, which we also modeled, we calculated recall and precision. Recall measures how many true attributes were captured by the agent, while precision measures how many attributes in the agent's model were actually true. We employed fuzzy matching using the Gemini 1.5 Pro model to account for variations in phrasing and manually verified a random sample of interactions to ensure consistency with human responses. We achieved a mean recall of 71.4% and precision of 72.5% for barriers, and a mean recall of 66.4% and precision of 84.2% for sleep goals. To validate our synthetic users, we conducted an evaluation with human experts who compared interactions from two types of synthetic users, one with comprehensive health and behavioral attributes and another with only demographic data. The evaluators, trained by a clinical psychologist, showed a strong preference for the full synthetic users, with statistically significant results and high agreement among raters. In our experiments on diabetes coaching, we recognize that diabetes is a common chronic disease affecting a significant portion of the adult population. Understanding the lifestyle barriers faced by individuals is essential for effective management of the condition. These barriers are influenced by various demographic and socioeconomic factors, which we aim to represent accurately in our synthetic user profiles. To create these profiles, we analyzed insights from 100 peer-reviewed articles that identified 246 challenges faced by cardiometabolic patients. We categorized these challenges into 6 subcategories based on the COM-B model, which helps us understand behavior in healthcare. We then developed synthetic users by utilizing data from the Project Baseline Health Study, which includes a diverse cohort of individuals. After processing this data, we focused on 345 type 2 diabetic individuals. To construct realistic synthetic user vignettes, we sampled from the COM-B categories and selected specific barriers. We then matched these barriers with individuals from the cohort, using their demographic and health data to create detailed narratives. We enhanced these vignettes with a coherent backstory generated by a language model, ensuring that the technical terms for barriers were not included, as users typically do not label themselves in such a way. Ultimately, we produced 200 vignettes using the Gemini 2.0 Flash model, chosen for its strong reasoning and conversational abilities. Section Summary. In this section, we describe the development of a sleep coaching agent utilizing a 2-agent system, where the reasoner generates an internal user model and the talker facilitates conversation, achieving 89.7% accuracy in identifying sleep concerns. We also detail the creation of synthetic user profiles for diabetes coaching, based on extensive research and behavioral insights, to ensure realistic interactions that reflect the complexities faced by individuals with cardiometabolic conditions. Section: The Diabetes Coaching Agent. In this section, we describe the diabetes coaching agent. We created synthetic users based on vignettes that interacted with this coaching agent, which was designed to help users set health goals and address specific barriers. After each interaction, the coaching agent identified one of the 21 barriers it modeled for the user. Both the synthetic users and the coaching agent were developed using Gemini 1.5 Pro. To evaluate the effectiveness of the synthetic users, we gathered feedback from a panel of 3 experts, including behavioral scientists and patient care practitioners. Each expert reviewed 25 randomly selected interactions from a total of 200. They found that the synthetic users were highly consistent, with a 92% agreement rate, and effectively represented the barriers they were meant to illustrate, achieving a 100% success rate. We also conducted a secondary experiment comparing our synthetic users to baseline synthetic users created solely from general demographic data, without the richer health data and specific barriers provided by our methodology. We ensured that both types of synthetic users had the same demographic information, communication style, verbosity, and confidence for a fair comparison. Human annotators evaluated 75 pairs of interactions to assess how well each type represented the barriers. The results showed that annotators preferred the interactions from our full synthetic users twice as much as those from the baseline users when it came to accurately representing a single barrier. Additionally, 70% of the annotators favored the full synthetic users for demonstrating the correct original barrier. While the baseline users were slightly preferred for informativeness, most interaction pairs were deemed similar. Overall, our analysis indicated that our synthetic users could consistently and accurately portray the original barriers in simulated interactions, which is crucial for improving the coaching agent's training data. We also examined the distribution of barriers represented by the baseline synthetic users compared to established reference distributions in the literature. The baseline users, relying only on demographic information, showed a significant overrepresentation of certain barriers, like physical capability and reflective motivation, while underrepresenting others, such as social and physical opportunities. This underscores the importance of grounding synthetic users in real behavioral data from the individuals the coaching agent aims to assist.